Okay, in our last video lesson, we talked a lot about how we're going to transfer from kinetic energy into potential energy or vice versa. So now let's break it down into these two scenarios, and let's start with endothermic reactions, okay? So endothermic reactions, endo meaning in, therm or thermic meaning heat. The biggest thing for these is to remember that anytime you have something that's endothermic, we're bringing energy in, and that energy is going to be stored in that bond energy, okay? So usually we get a transfer of kinetic energy to potential energy, and then it stores it as that bond energy, okay? So it's kind of like a savings account where maybe you got paid to mow a lawn, or maybe you did a babysitting job, or maybe you have like a job that you get paid weekly, or maybe you just get an allowance. And when you get that money, if you put it into a savings account, you no longer can use it, right? You have it, it's stored, but it's not being used, okay? So using money and spending money is kind of like kinetic energy, where storing it in your savings account or on your PayPal or your Venmo balance is like unused money. It's there, but it's not doing anything, okay? So typically what we see happen is that during that process, energy gets stored as potential energy, so they get it from kinetic. So it typically cools down, okay? This graph over here is kind of helpful for that, where before the reaction, you have a certain amount of kinetic energy, a certain amount of potential energy, and a total kinetic energy. And then after the reaction, the kinetic energy decreases, so it gets colder, and then we stored more energy as potential energy in that process, okay? Now, we do need to talk a little bit about what happens if we have a process where there is no temperature change, okay? Those things do happen. We do have processes that do not have a temperature change to them. In that case, if you're looking at something and it's a reaction or some sort of physical change and there is no temperature change, you probably can identify an external source of energy. For example, maybe you have electricity hooked up to it. Okay, so maybe you're running a reaction and the electricity is providing energy. Or maybe you have something that's reacting and you have it on a hot plate. Or maybe you put it in an ice bath, okay? So we can externally change the total energy so we can keep the temperature the same or keep kinetic energy the same and still mess with our potential energies, okay? So don't fixate too much on the fact that it's gonna get cold. Yes, if you leave everything alone and don't let the environment play a role, yeah, it'll get cold because it's gonna steal from a kinetic. But there are scenarios that we can still have an endothermic reaction that we may not see a temperature change. In those cases, you really have to go back to the definition, okay? If you're endothermic, that means energy has to be going in and being stored in those bonds, okay? So always ask yourself the question, is energy being put into this or is energy coming out? If energy is being put in, we tag it endothermic. A great example of that is phase changes. So when we go from a liquid to a solid or a gas to a liquid, we melt, boil, freeze, condense. Those processes do not change temperature, but there's definitely an energy change there, okay? So let's talk about melting or boiling because they're both the same, okay? We've already established that boiling is an endothermic process in previous units because we said boiling is a cooling process, right? Because the highest energy particles leave first, so the particles that are left are colder than the original ones. So yeah, we have a process where if you want to boil a liquid, you need to put energy in. But because the highest energy particles leave, we're changing mass, okay? They're leaving that system, they're leaving that area. The overall energy doesn't show a decrease in temperature because we're constantly heating that up, feeding it energy when you try to get something to boil, okay? We did see it get colder when we boiled it using the vacuum pump. So we do see in that case, when we didn't have a burner on it, it does do that. Even with melting that happens, right? If you melt a solid into a liquid, to get that to happen, you need to put energy in, okay? So energy goes into that. It doesn't change temperature because all that energy is being used to rearrange those bonds and break the IMF and allow them to start to flow next to each other. So instead, it draws energy from some sort of external source, like the air around it or something like that. So we don't see a temperature change in those scenarios, okay? So it's okay not to have a temperature change. Normally we do, and it's gonna be really nice when we do, but there is cases where we don't, okay? The opposite of that, obviously, is exothermic, okay? And we don't need to spend as much time on it because it's just the opposite. So exo meaning out, therm or thermic still meaning heat. So now we're taking energy out of those bonds and we're using it, okay? It's like you're going to go to your Venmo account and you're going to send money to somebody and you're going to use that money, okay? Or you're going to withdraw money from your savings and you're going to pay for something that you want to buy and use, okay? So anytime you have a process where there's unneeded energy from the original bonds, that gets released to become kinetic, okay? Again, we see this graph over here where potential energy was high, kinetic energy now low, and then afterwards the potential energy goes down because we don't need as much for whatever's afterwards, and the kinetic energy increases. So there we would see something warming up in our scenarios, okay? Once again, if we don't see a temperature change, that means the extra energy is used in another way, okay? There's other ways it can happen. Usually from chemistry, we're tracking temperatures, so usually it is going to be a temperature change, but there are scenarios where we may be using that energy in a different way to make that happen. And again, kind of like our phase changes. So when you freeze something, okay, this seems really weird because freezing water for us feels cold, but when you freeze something, you actually are an exothermic process. Because to go from a liquid to a solid, solids need less energy. So they actually are a reduction in potential energy. So there is some sort of let off of kinetic energy that leaves that system and goes someplace else, okay? We don't see a change in temperature because, again, all that changeover is affecting that IMF and reforming and recreating new structure, which is kind of absorbs that or deals with that instead, okay? So yeah. Well, that's our exothermic, okay? We should be able to distinguish between exothermic and endothermic in everything that we do in this unit. Now, one thing we want to talk a lot about in terms of our reactions is what happens during the actual progression of the reaction, okay? So what happens as the reaction proceeds? And there's some key things, and sometimes these are actually opposite of what you may be thinking initially, or maybe you may have a misconception. So let's talk about the progression. Okay, we start with reactants, and reactants, they're fine, they're stable, they're whatever they are, but to get them to react, to get them to break their bonds, to get those bonds to break, we always put in energy. Always. Always, 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 always. Okay? We always have this energy input that happens. For some reason, I've had students over the years tell me that breaking chemical bonds releases energy. It's completely false. The breaking of the bonds does not release energy. Okay? The breaking of the bonds, you put energy in. It's called activation energy. Even reactions that we think don't need any activation energy because they just happen naturally, they just happen spontaneously, well, they happen at like room temperature or a little warmer, a little colder. So just because they're not at absolute zero, because they're in an environment that has available energy, we don't see the energy being used, but the energy does still go into them to cause this reaction to happen. Because substances have energy, they have their own kinetic energy just because they have a certain temperature. So sometimes they actually kind of contain their own energy that allows them to use it to then react. Okay? Seems kind of weird, but that's how it works. So the trick is always put energy in to break the bonds. So once we've broken the bonds, we now have a bunch of things that the bonds are broken, they're all disorganized, and then we restructure or put things back in place. Well, when we re-put things back in place and we create new bonds, we always release energy, okay? So the formation of bonds is a releasing of energy, okay? So there's always this give and take between you put energy in to break them, and then when you make new ones, you release. So I think what happens is, like maybe some of the other sciences, like the biological sciences, may just say breaking chemical bonds releases energy because they may not focus on the fact that it's actually kind of a two-step process. Where step one, you break them, put energy in, and step two, you build new ones and energy gets released, okay? So for chemists, we want to compare what's the potential energy before versus the potential energy after, because this comparison will tell us if it's exothermic or endothermic. So we actually can look at potential energy numbers and graphically look at that, okay? Ultimately, in nature, the lower the bond energy or the less potential energy we have, the more stable something is. So unless we try to like fight against natural tendencies, the natural way for chemical reactions to run is always to go to lower energy, okay? Which means exothermic reactions tend to dominate our world. Okay, let's go look at a couple graphs. So graph number one, an exothermic graph, okay? Now keep in mind, we are tracking potential energy here, okay? Sometimes students say, well, Mr. Dirksen, how can this be exothermic if it has less energy afterwards? Shouldn't like exothermic things make things hot and like have more energy? Yes, but remember, the potential is the stuff we don't feel. The potential is the stored stuff. So if we actually look at this through the lens of potential energy or bond energy, or the actually energy inside the reactants, they start here. That's their bond energy. And we first need to put energy in, okay, to activate it, to break these bonds. And then once we broke the bonds, then we can form new products. And as they're forming those new products, that's when we get a change in energy that is releasing energy, okay? So we are inputting energy to break the bonds, we're releasing energy to form the new bonds, and then our net change is a negative energy change, okay? And negative energy change is a release of energy, okay? So where does this excess energy go? Okay, well, if it's not being stored as potential energy anymore, it relieves as kinetic. That's why exothermic reactions feel hot to us, because we're on the outside, or whatever the thermometer is on the outside, and as those reactions run, the new products need less energy than the original reactants do. So as a result, there's extra energy that can be given away, and you give away energy as thermal energy, okay? Because it's moving energy. You can't give away potential, it's stored. You need to always give it away as kinetic. So that is moving energy or heat energy. So that way that extra energy releases as heat and it warms things up, okay? But take home is we still need to put energy in to break the bonds, and then there's a release of energy to make the new ones. Now in this case, water would be more stable because its bond energy is lower than the original reactants. So we would expect if we put hydrogen and oxygen together and gave it a little bit of activation energy, we could get them to react, which is why hydrogen is explosive in oxygen. We can flip it, okay? Believe it or not, there's a way, and I'll probably show you in class if I can get a demo going for this topic, where we can make hydrogen and oxygen turn into water also, okay? Flip it around instead, where the water runs in reverse and makes hydrogen and oxygen, okay? So in this case, we start with low potential energy, and we need to give it a lot of, we need to give it a lot of activation energy to get the water to break, so it's less likely to happen, but we can get it to happen, and then we can form new bonds, and we're gonna make some hydrogen and some oxygen, okay? So in this case, we have a positive energy change, which means it's endothermic, because we're absorbing energy overall, okay? So where does it come from? Well, if we're absorbing energy, it has to come from someplace, okay? If we don't have an external source, that energy has to come from heat or kinetic, so it'll cool down, all right? The demonstration I'll show, we're actually going to find an external source. We're actually going to use electricity to make this thing happen. But if without the electricity, we would have to somehow get it to actually absorb it from the kinetic world, which doesn't happen readily. So this is not real common to happen unless you actually force it with some electricity in our stuff, okay? Take home is, for endothermic reactions also, there's an activation energy to break the bonds, and then we release energy to form new bonds, okay? So exothermic and endothermic both have activation energy. They both require energy input to have them happen, okay? Always, always, always. Energy in to break bonds, energy out to form new bonds, okay? We're gonna end the video here and then move on to our next topic.